In this video, we are going to do an example finding a line integral of a vector field. So the problem says, given this vector field f, find the counterclockwise circulation of f around the circle of radius 3 centered at the origin. So let's just get it started together to make sure we know what these terms mean we're doing, and then I'll give you time to try it. So the problem says find the circulation. So this is a term that we saw defined in the last video. Circulation is a type of line integral. So it's a line integral over my curve, C. Take the vector field, and then my notation for a line integral of a vector field is you say this, and then you dot it with dr, my position vector. So we're doing a line integral of a vector field. The term circulation refers to the case where our curve is what's called a closed curve, which means it starts and ends at the same spot. So let's also draw a picture of the curve. So if I draw my axes, draw y-axis, draw x-axis, and then we have this circle of radius 3, circle of radius 3. Okay, and we're going counterclockwise around it. So we are traveling in this direction around it. So that's going to be important. When I find my parameterization, we will want to make sure that it is going in this direction. Okay, so at this point, pause the video to try it for about 5 minutes. So pause it in 3, 2, 1, and try it. Okay, so hopefully you did that. Hopefully you paused it to try it. Let's talk about it. So remember that the way we get something like this started is, first I got to parameterize my curve. So we have to parameterize the curve. Okay, so to do that, I can first write down the equation of the curve. This is x squared plus y squared equals the radius squared, which is going to be 9. And then similar to what I've done with ellipses, to parameterize those, let's divide the 9 over to get a 1 on the right. So that'll give me x squared over 9 plus y squared over 9 equals 1. And then I can write these fractions as perfect squares. So this is going to be a perfect square plus another perfect square equals 1. In the first parentheses, we would have x over 3. In the second one, we'd have y over 3. Okay, and as we've seen before with ellipses, to make this work, this kind of looks like cosine squared plus sine squared equals 1. So we can let x over 3 be cosine of t. Let y over 3 be sine of t. And then if I isolate the x and the y, we get that x equals 3 cosine t, and that y equals 3 sine t. Then we have to write down our domain for t, so I'll put a comma. And to go all the way around the unit circle, we go from 0 to 2 pi. 0 to 2 pi. The one thing I want to check quickly is this in the correct orientation, the correct direction? So I can check that out by plugging in a few test points. Like if you plug in t equals 0 into the parameterization, you're going to get that x is 3 and that y is 0, which puts us here. If you plug in t equals pi over 2, it turns out that you'll get the point 0 for x, 3 for y. So that puts you up top. And you can check if you plugged in points in the middle, between 0 and pi over 2, you're somewhere here. So overall, this does seem to be traveling in this counterclockwise direction. But that is important to do a reality check on. It actually turns out if you switch these, if you let x over 3 be sine, and you let this one be cosine, it turns out it's actually going the opposite direction. And when I have a line integral of a vector field, that direction of travel does matter. Okay, when we have a line integral of what's called a scalar function, that's when I just have a function. It's not a vector field, it's just a normal function, ds. There, the direction does not matter. Okay, so, all right, so let us now substitute in. So subbing in, I'll convert it to a normal integral, where t goes from 0 to 2 pi. And now what I have to do is, I have to substitute in my parameterization into my vector field. So I will have to write down f of, sub in my position function, I'm going to call it r of t. That's going to get dotted with the unit tangent vector, t hat. That's going to get multiplied by ds. Remember, the unit tangent vector is the velocity vector divided by its length. And then ds, remember, is the length of the velocity times dt. So the length of the velocities cancel, and I'm just left with the velocity on the numerator and then a dt here. So I'm going to need to find the velocity. So let's do that. So my velocity vector, we take the derivative of these position components. So the derivative of x is -3 sine of t. The derivative of y is 3 cosine of t. Okay, so now let's plug in. So I got my integral from 0 to 2 pi. And this f of r of t means take the parameterization for our position and plug these in to our vector field. So for x, I am going to plug in 3 cosine t. For this y, I'm going to plug in 3 sine t, and that'll give me that vector. So plug it in for x, I'll get 3 cosine t, comma, plug it in for this y, I'll get 3 sine t. Okay, so we're subbing in our parameterization. That should get dotted with this velocity vector. So dotted with the velocity vector, -3 sine t, comma 3 cosine t, and then a dt at the end. Okay, so we're getting there. We're ready to take the dot product. So we have the integral from 0 to 2 pi. So you multiply the x components together, and we'll get -9 cosine t sine t, plus, now we multiply the y components together, and we'll get 9 sine t cosine t dt. But I notice these are perfectly opposites. So they will cancel and give me 0. So I just have the integral of 0. Visually, what that means is if I drew my graph, the graph of just y equals 0 is just a horizontal line segment on the x-axis from the point when x is 0 to when x is 2 pi. So that area between the graph and the x-axis, that's 0. There's no area. So this integral is just going to be 0. Okay, so that's kind of nice. It made the calculation quite quick. So later in our course, we'll actually see an even quicker way to do something like this when I have a line integral like this over a closed curve. So in terms of our goals for this section, we have finished our last goal, which is how do we define and calculate what are called the flow and the circulation? So this is when our vector field is what's called a velocity vector field. In the special case, when I have a closed curve, we call this line integral the circulation.